Yeah, so I've got a bunch of these JBL EON 510s come in. They've been collecting them for years. This company uses them for soundproofing to test the soundproof between rooms. They set a load of these things going, blasting out loads of pink or whatever noise spectrum they want, and then they test the sound levels to prove that they've done their design correctly. So it's from the City of London area somewhere, an architect stroke soundproofing company. And JBL 510, I don't really bother with them because they're kind of marginal. They're getting a bit old now, but there's a whole box of them. You can't see it, but over there's a box with a 5 or 6 in. How many is that? There's 6 on the paperwork, but I can only see 5. And I just thought I'd give you a bit of a rundown because I couldn't find a schematic for this, but it's very similar to the JBL EON 315. The schematic for the power supply and the amplifier is very, very similar. And also very, very similar to the EON 210P. So if you get stuck, you can look at the schematics for those two. But it's got the same basic components. If you looked at the other overviews I've done of this range, it's got the same input circuitry, it's got the PTC. If you want more detail, look at the 515XD or the 315, that's got more detail on it. But I just thought I'd give you a pointer because there is a very strange faults manifest on these, and you can't really easily tell what they are unless you stumble across it, I found anyway, and I've done a few, so I thought I would share it with you because it might save you a lot of time. But you've got the mains input, the filtering here, you've got the positive temperature coefficient thermistor there, which is on switch on when the 5 volt comes out, is shorted out by this relay, and this one's the voltage doubling relay, so there's a comparator circuit in here that detects whether you're connected to 110 or 220, 240, and then switches in the doubler circuit, which just closes the contact on the bridge rectifier to the center point to get halfway doubling of power stored into those capacitors. Now, what these have got, this, I don't know if it's doing it at the moment, it's not doing it at the moment. Can you see this? This is the mixer. I've taken the mixer off. The mixer's got about 18 or 19 chips on there. They're all the same op amp. If you're fiddling with these, put some tape on the annunciator wires. But quite often the amplifier kind of works for a while, but in certain conditions it will shut down and all 3 LEDs come on. You end up with the blue LED, the limit LED, oh sorry, 3 of the 4 LEDs come on, so it's the power, the sensitivity and signal present come on. So those 3 LEDs are hard on, okay. But if you measure the voltage, you think, well, is it a power fault or something else going wrong? What there is the secondary of this power. This circuit is dealt with on the 315 video. It's the same as far as I can tell. So if you've got a problem over here in this buck regulator that runs off the raw rectified DC, produces the 12 to 15 volt rail for the electronics to work over here on the high side of the power supply. The end of this cap here is the AC 0 volts, and there should be 15 volts on there. This coil often starts to leak or goes short circuit, or the LNK 302 chip blows up. So when I service these, I always change these two anyway for a high voltage version of that. But anyway, so if you then zoom in over to this part of the board over here, you can see, where are we? Touch, I think this is turned on, by the way. It's not fully screwed down at the moment because whoever's sent it in has been poking around with it, and it's not screwed onto the heatsink. The screws are in a bag. Alright, so on the secondary side, the DC side that powers amplifiers, the plus or minus 40 volt rail, which powers this basically almost symmetrical 2 power drive channels. And these power drive channels are quite reliable, but if you've got the lid off, this thing, and this end, this is the power. If you've got the lid off, then while you're in here, it's like changing the oil on your car. You'll need to change that cap there, C102. Anyway, the one next to the resistor, that one, and the corresponding one on the other channel, which is that one. Right? I've already changed that one. So change those 2 caps, right? Because if you don't, it'll be back in the workshop in weeks, I found. So that one, and then the same one over there, all right? So change those 10 microfarads, 10 microfarads, 16 volts. That's the capacitor that the high side supply for the high side FET switch on the half bridge is derived during switching, is rectified and derived, and that cap there is the reservoir capacitor for the high side switching voltage. You've got two N channel FETs there, and one of them's going up and down with the load. Okay, so yeah, change them caps while you're in here, just as a side point. I forgot what I was saying now. Anyway, so they're the amplifiers, are symmetrical, and then they take plus or minus 40 volts. This is generally a pretty good design, except it's let down by a few components, namely this coil doesn't have a voltage rating. If you look at that coil car 335D, doesn't have a voltage rating. Change it for one does have a 300 volt or 400 volt voltage rating, because you can see them break down. You can see them arcing when they fail between the bobbins wound around, and then obviously a wire comes out from the inside and out to the terminal, and it arcs across somewhere inside, and you can usually see it arcing. Or sometimes the amplifier will be working absolutely fine, then you'll hear it through the speaker and a little whiff of smoke or even a spark. You can see a little arc in there. So change that and change the LNK302. If you're using these for gigs, change them. If you just listen to them and you don't want if they blow up, don't bother changing them, right? So anyway, where are we? Yeah, so these test points, look, I'll zoom in a bit further in case you're looking on a phone, up to the point where we lose focus. That's there, so back a bit, back off, back off. So what have we got here? We've got test point 602 is ground. If I adjust carefully and dangerously. Right, well, I want to read these voltages out. You have to take my word for it that I'm telling the truth. I have no reason to lie. So ground point on test point 602. And we've got 58.5 volts. Oh, sorry, no, hold on, that was millivolts. We've got 38 volts on this rail and 38 volts on that rail. And you'd be thinking this is working okay, all right, but they'll work for a while. And I think this fault generally gets worse as you go along. As you ignore it, people say, oh, I used it for an hour and it packed up, and then it broke out, and then I was turning it up. When I turn the sound up, the volume starts to go. Or it went off, and I looked, and all these three lights, three of the LEDs were hard on all the time on this on the mixer board. All right. Now, I have seen these in various states of decay, and I know what it is, because obviously I've worked on them for ages, but these have been worked on by an engineer and he couldn't fix them, right? So there's clearly some people don't know this fault, so I'm going to lay it out for you so that you do know this fault, right? What we've got, if we just move that, if I just turn that off at the moment, that's taking 36 watts at the moment on quiescent standby. There's no audio going through it at the moment, right? So inside the unit we've got, what have we got? On the back of these invoices, there's the rectified mains, the bulk, we'll call that the bulk. So that's something that's normally around about 360 volts DC, right? Then you've got your bridge rectifier, not volts AC line. Again, DC across here, and then obviously we're going to draw the whole thing, but I'll draw it anyway because you might want to see it. Basically your standard bridge, and your mains comes in here. I think we've got a PTC in here, PTC, got a relay across the PTC there. That has a coil, obviously, as relays have coils, and the coils is closed by the plus 5 volt DC on the secondary side. So if the 5 volt secondary side doesn't boot up and start, then that relay won't close. This positive temperature coefficient resistor will continue to heat up and then basically go high impedance. And when it goes high impedance, it's acting as like a resettable fuse. And before the relay closes, it also acts as an inrush limiter because it's got a residual resistance of about 20 ohms or something. So it's quite a clever thing. So when you turn the unit on and the lights don't come on, then this PTC, the positive temperature coefficient resistor's gone high impedance, all right? So there's live and there's neutral. There's also actually a bit of a strange thing on these. There's a couple of voltage dependent resistors here which aren't on any of the circuit diagrams, and I'm not surprised because it's a bit of a questionable thing, syncing mains transients to ground through varistors. So voltage dependent resistor, and this, the center tap part of this goes to the supply ground. Trouble is, if you had an earth fault on your lead and a big transient came down the mains, you get it straight onto your microphone, which I wouldn't really like. It's happened to me once before. I didn't like it then either. Right, so we've got V-bulk 360 and 0 volts AC. Now, in here we've got a couple of caps, electrolytic aluminium, 25 millimeters by 53 millimeters, and they're 1200 microfarad, 200 volts DC caps, right? And they're connected like that. Now the problem with you connecting capacitors like this is that normally they would have a very low leakage current, but if the leakage current, the DC leakage current leaking through these capacitors is not equal, then this DC voltage here will drift up and down depending on the leakage current. And the nominal way they control this is by having a couple of resistors there. So you've got those two resistors in there. I don't know what value they are. Are they about? I think they're about roughly about 100k. You should be able to track those down. Can't remember from memory. And the idea is that there is some current going down here. There's a current going down here, and this acts as a potential divider. Divide this into and to stabilise this DC voltage. Right. Now there's a bit of a strange circuit on this because let's get my head around this properly. You've got your, if we just draw the, so that's V bulk and 0 volts AC, right? So if we just draw the transformer, the primary of the transformer is connected to, so the primary of your switching transformer, so that's the prime, there's a transformer, look, and then on the secondary there, obviously, you've got your rectifying circuits and so on going off to your DC supply for the amplifiers and everything else. All right. Now, what you've got on this is one end of this transformer is connected to that point, right? So there's no copper connecting this end of that transformer. This is done for efficiency. And also to make it drive. If we didn't have to drive from 110 volt supply, it'd be a lot easier, to be honest, and more reliable, but that's obviously designed for the American market somewhat. So what you've got is one end of the transformer is the primary transformer. Of course, you've got to switch the current in that transformer through a half bridge, and then the other end of this transformer goes to a capacitor. Which capacitor is it? Is this turned? No, it's turned off. It's that one, that cap there, right? The other end of that transformer goes to the capacitor, and then it goes to the. I'm not going to bother drawing the push-pull half bridge setup, but basically, if you can imagine, this is being driven between. There's a variable pulse width ratio, mark space ratio, or duty cycle if you like, between V bulk and the north side is 0 volts going into this capacitor via the half bridge. Right, so there's your half bridge down there, driving the end of this cap. That value I think is 100 nanofarad, is it? I think it's something like 100 nanofarad. That cap actually is a self-healing cap, and they can heal themselves away to nothing, because obviously this is going at 75 kilohertz or thereabouts. Right? So that cap can heal its way to nothing, so there is a problem with that when you have high loads, that there's not enough capacitance residual, because it's a polycarbonate film or polyester film metallized with a vacuum deposited aluminium coating usually, and when it sparks through it melts back and self-heals, but if it keeps breaking down it'll just carry on self-healing itself to a very low value, and eventually the power supply won't run properly. Alright, so there you have it. So basically there's no copper, there's only the paper capacitance connections between the power supply and the drive. Obviously the drive has taken this line and this line into the drive, so V-bolt goes in there, got it VB, and 0 volts going there, and there's all sorts of control circuitries and the half bridge driver in there. It's driving that line up and down, 75 kilohertz, and as you design more power there's feedback via an opto from this side which goes in there, feedback to control that. Alright, now looking at, that's the circuit you've got. Alright, now all sorts of things can happen with this. You can have a minor leak in your capacitor, so these become out of balance, and bearing in mind that these are 1200 microfarad 200 volts, and if the leakage of this one, the leakage should only be in the order of microamps on these caps, even that, probably 1 microamp, probably, or 2 microamps. But if say this one's leaking 3 microamps and that's 1 microamp, this DC voltage taking this network in, as I say, you've got basically a parasitic resistor being introduced here or both, and there is a parasitic resistor in there all the time which represents the leakage impedance of that capacitor at mains voltage, and if these start to vary because the capacitor is aging or drying out or leaking slightly, this DC voltage can go up and down. So instead of having half of V-bulk on there, you can have everything between, it can be between, well, if the capacitor is completely short it'll be 0 volts, won't it? And if the capacitor is leaking slightly, it can be anything between, and this one's not leaking and that one is leaking, anything between 0 volts and V-bulk. Anywhere in that range it could be. And when these caps get old, these things start to leak, and they do strange things in different temperatures. They get warm and then they start to break down, and then they, whatever it is, shorts out or fizzes away, and it goes away again, and it will gradually get worse. You'll get some weird behaviour. Now what you've got to be careful of is that when you repair these things is that you take them apart and you think, oh well, the power supply is working fine, but it's something else. And quite often I've had this half bridge blown up because it's struggling to maintain output as demanded by the secondary side, and yeah, and you change it and you think, well, that's great, I've changed the thing, it's working, but again it goes up into the field, gets warm, slightly different mains voltage, varying mains voltage, this starts to drift out again and you're back to square one. So you really have to be quite convinced that these big reservoir caps are okay, not on their way out. Basically, if you touch one of these things, check those caps. They're about £4 or £5 or $5-6 each, these caps. I've got them in stock, so if you want some, let me know, because I bought a massive box of them. Because that they're 25 mils, I said, diameter by 51 or 52, and that's not a common size and not easy to get hold of. Radio Spares in the UK or Farnell don't sell them, alright, so, but I've got some. So what are we saying? What am I saying in a roundabout? I'm just giving you the background to this problem, alright? So you open this up quite happily, and all three of these lights are on, but the you've got your plus or minus 40 volts on your test points. So why are the lights on? Well, then you check the 5 volt rail and you see that the 5 volt rail, the plus or minus, this runs from plus and minus 5 volts, okay? So the plus or minus 5 volt rails, maybe one of the rails is not quite right. So you automatically assume that there's been a transient or something, or one of these chips has blown up. Each channel of these chips, there's a twin op amps in these, and each channel takes about 1.3 milliamps quiescent on each channel. So, you know, if you bulk up all the, you count the channels, count the chips, multiply 2, multiply 1.3, it comes to about 60 to 70 milliamps. So this board, when it's working, and it's a good test actually, if you unplug this umbilical and then put plus or minus 5 volts on those pins at the end and ground, I can't work out which way around they go, but it's pins 9 and 10, and I think 8 is ground, or 7 is ground. If you, oh no, it's this end here, look, that's where it is. So there's the 2 rails on this end of the connector, this pin, these 2 pins here, those 2 pins there, and the ground pin is one of those, but you can buzz that out, can't you, anyway? So the ground pin. So anyway, plus or minus 5 volts and 0 volts on there, and the rail should take, when there's nothing plugged into it, and it's you just powering up independent of this, the rails should take between 80 and 95 milliamps. All right, I've measured enough of them to know that if you measure the current going in here and it's not 80 to 95 milliamps, say it's higher than that, you've instantly got a problem with one of the chips. They should take about 90 milliamps, this board, on each rail. All right, so on this one, the lights were all on when I took it apart, and I checked this out with a cable I made up somewhere. I've got it here, but it's just an IDC connector with a 10-way ribbon on the end, clipped onto the dual rail power supply. And yeah, you should get 90 plus minus 90 milliamps approximately. You know it's working. So then you can say, oh, well, it's not. Now bear in mind the amplifier seems to work, but these 5 volt rails aren't working very well, are low. And what it is that the 5 volt rail on this, there's a rectifier, then these 2 caps, that's plus or minus 5 volt smoothing capacitors, and then under here, there and there's a TO92 package, which is a plus or minus 5 volt regulators, the 7905 and the 7805. Okay, now they take what's supposed to be 12 volts and then regulate it down to minus 5 and plus 5. But this seems to be working, but you've got a problem with this, and I've seen people send them in with faults and they've changed chips on the mixer, been bogged down in the mixer because they can't get the mixer LEDs to go off. And what it is that this power supply is struggling and giving a strange waveform, and there's no feedback from the winding on there for the 12 volt. 12 volt is an independent winding for the mixer supply, but there's no feedback from that. The only feedback going back into here is from the plus or minus 40 volt rails. All right, so the plus or minus 40 volt rails will read okay, and you'll get some output too, but the shape of the waveform, because there's very bad smoothing or very bad asymmetrical drive for this transformer, it affects this rail badly, because these regulators will drop out at about 7 or 8 volts. So if at any point the flux in this transformer drops below what it should be because it's not being driven properly, then it could be asymmetric drive to the transformer, or that capacitor is gone. All right, so I've seen several, well, I don't know how many over the years, of amps that someone's given up on. They can't find out what's wrong, and what it is the centre point of these capacitors, the actual midpoint voltage on here. Sorry, this is no soldering and buggering around, but this is just giving you the lowdown on what to check and the explanation why. So if these 2 caps aren't like tip top, then you can get all sorts of problems. You can blow the output stage, you can get them dropping out during performance. Put them on the bench, they seem to work. They do become somewhat temperature dependent, and of course it will get worse until it fails, and when it fails it can blow up everything else. So that's what's wrong with this one. Of course, if one of these starts to leak, right, you take it apart and one is leaking, and this voltage has gone up to say 100 volts across there and 260 across there, then this has been stressed as well. So to get this to balance properly, you do have to change both caps, even though one of them seems to be alright. Okay, don't make the mistake of just changing one of them. So that's the bottom line on that one. It's an AC drive circuit from this. It's a strange circuit, and working on 220 volts AC. On 110 volts, then this point here is connected to there, a voltage doubler. It doesn't matter on 110 volts. It's only us 220 volt Johnnies that get this problem. So change those caps, And don't, because the power supply reads okay here and here, sorry, the the plus and minus 40 volt rails look alright, they're not alright, okay, because the 12 volt rail, that's for your plus minus 40, the 12 volt one is taken off a separate winding. And if this starts to become asymmetric in drive, i.e. these voltages get out of balance, it's this one is the detector. You'll see what you'll see if you look on the, there's a diode, there's two diodes back to back, obviously that's the plus 12, and there's another diode that way around, it's the minus 12, and of course they go off to two different caps. But if on the scope you see something like well, just basically a lot of ripple like that going on that rail, dropping down, or it might go down. If you get a lot of ripple on the 12 volt rails, then get a meter out, measure the voltage across these two caps, and it should be within a few volts, it should be the same. And if you measure a different voltage on either cap, more than say 10 volts out, then it's going to blow, and it's not going to work properly. Also, what you can do is warm this up for a few minutes with a hairdryer and just watch that voltage go all over the place, and you know that these caps are going to be a problem for you. Alright, so I've got the caps, I'm going to change them. This is probably the end of the video because I've got to get on with these, but that is a useful tip. Always check those caps, and even though it seems to be working, measure the voltage across there to make sure it's the same. Alright, and then you might get straight to the heart of the problem. And don't repair the power supply and fix it unless you're confident these caps are good, because it will work but not for long. Okay, so if you could subscribe just by pressing the button down there. This is of course for the JBL 510, and it's also applicable to the JBL 515. It's applicable to the EON JBL EON 315s. The EON 210p are all pretty similar. Okay, so good luck with yours, and I hope you found that helpful.